Hello, everybody, and welcome to Data Science Foundations. So we're at the kind of like wrapping up part of the class right now. So we've hit certainly the climaxes of the class. So we understood the plugin principle and how we could use the plugin principle to construct confidence intervals for any measure that we wanted, as well as its relation to random variables and how we can make random variables of real life situations, like simulating randomness, and how both of those can be incredibly useful. We What we've also done is we've talked about the bias variance trade-off. We've talked about the generalization approximation trade-off, and what they mean for machine learning. And this is incredibly important. So these two climaxes, the plug-in principle, and then this climax with the bias variance trade-off, which is kind of like it sort of falls out of this idea that if you have a rare event and then you have the opportunity to have this rare event many times, then this rare event becomes not so rare. There's quite a high probability of seeing this rare event. It's sort of like one of these fundamental ideas in life, where the plug-in principle is also one of these fundamental ideas in life. So we should really understand the bias variance trade-off and the generalization approximation trade-off pretty well. We understand, at least at the first level, why it happens. One of these good tricks to see if you understand something is if you tell somebody about it, they ask you why, you're able to supply an answer. They ask you why again, and you're able to supply an answer. And maybe if you do that maybe 5 times, still able to apply or still able to answer correctly, then you probably understand it. And I think we could probably do it just once, at least for a couple of things. So let me sort of highlight the key principles of the bias variance trade-off. So principle number 1, and this is the bias variance trade-off and approximation generalization trade-off, just sort of rephrased here. More complex hypotheses have a lower in-sample error, or more complex hypotheses will have a lower bias. Now, why is this true? I think it comes down to a fundamental principle that we all sort of understand, and that is something that is more complex can be more expressive. So think of something that is less complex as just a hammer, and think of something that's more complex as a full toolbox. So if you know the exact problem that you're going to be working on, you can obviously, and you're able to sort of change the way that you work on this problem, to the smaller details. You can obviously do anything that you could with a hammer, with a full toolbox and more. So certainly you're going to have it at least lower accuracy on things where you can change your procedure, right? So on the things you know about. So another way to think of this a little bit more mathematical, especially for the lower bias case, is if you have a set of hypotheses that encapsulates another set of hypotheses, there's no way that you could have a lower bias. Remember, bias is the absolute best accuracy that you can get if you knew the full training set. So there's no way you can get a higher bias, bias being the error in this case, because you actually contain the hypothesis from the smaller hypothesis set. So the worst you could do is just select that, but there's a chance that you can select something even better because you have more hypotheses to choose from. I think this makes sense. I think that this is sort of like a foundational human thing. I don't think I sort of need to explain this anymore. But the second thing, we will need to explain a little bit more. So the second part of the bias variance trade-off, the second part of the approximation generalization trade-off, is that more complex models have higher variance, and more complex models have higher generalization error. Why? Okay, you should be able to answer this, at least the first why. So I'll give you 1 second. You can pause the video. Okay, so why does this happen? So this happens because, as we talked about, this second fundamental idea, there's a rare event that can happen with your hypotheses, and this rare event is that a hypothesis misrepresents itself. So one hypothesis misrepresents itself. So it will represent itself as really good on the training data, whereas it's not really good on regular data. And this is even in the case where we've taken IID samples. So we've got a random sample for our training data and our test data. So they come from the same distribution. They're just random parts of the same distribution. Okay. Um, So, I mean, that's kind of why it happens. So in this case, there's this rare event, which is that a hypothesis will misrepresent itself. Because we're searching through many more hypotheses, there's a higher chance that this rare event will happen, and therefore it has higher variance, right? There's a higher chance that you'll get one of these misrepresentative hypotheses. And why would you choose one of these misrepresentative hypotheses? Well, by definition, it does really well on the training set. Right, that's one of the parts of this misrepresentative hypothesis. It does really well on the training set, much better than it would do on the test set. Okay, that's fine. But here's a question. So why how can, I guess this is more like a how question, how can a hypothesis sort of misrepresent itself, right? Why do we have two sets of hypotheses? One hypothesis that will not misrepresent itself and another hypothesis that will misrepresent itself, right? So we're learning from the same data. How can it be possible that we have one hypothesis that misrepresents itself and one hypothesis that doesn't misrepresent itself? It's a little bit strange, right? If you're learning from the same data, if you're taking in the same patterns to an extent, sorry, I should probably scoot this up because the answer is right here. So how do you mess up, right? Shouldn't all of them mess up, right? And this is sort of the idea. If you necessarily got a bad training set, so if you got a training set that's not representative of your test set, then you'll have lots of hypotheses that mess up. But let's say you've got a good training set. This is one of our first assumptions. How can you mess up? To me, this seems a little bit odd. How can you mess up? Well, the answer is noise. So the real answer is that the hypothesis will do one of two things. It will fit to the real patterns in the data, or it will fit to the noise. So let's go on. Let's explore what noise is. What am I talking about here? I'm talking about two things specifically. So let's check out a data set. So we've got a data set here. So this is the Lagrange polynomial. So in this case, it's a second order, parabola. The x's sort of being -1 to 1. The y is going all the way from -1 to 1, or something around that point. Pretty simple. Let's add some noise to this data. So we add some noise to this data. It looks more like this. It doesn't fall exactly on the line that we were talking about. So instead, a little bit up, a little bit down. We can see how there's noise here. So this is one type of noise. So what can happen is that you'll get just a couple of points, maybe this point that doesn't really fall on the line, or this point that doesn't necessarily fall on the line. And there you have it. You'll fit to something that doesn't necessarily fall on this correct formula, this target function, because we fit to the noise. Because we've got such an expressive, such a large amount of hypothesis sets, it's very likely that one of them, instead of trying to fit to this true polynomial, will instead fit to the noise, get a much better score on the training set because it's fit to the noise, and therefore misrepresent itself on the validation and test set. There's a second type of noise that I want to talk about. So what we call this noise is we call this stochastic noise. So there's one more type of noise that I want to talk about here. And I'll show you later on that empirically it's the same thing. And here's the second type of noise. This might be a little bit confusing. So you may have seen this before. This is just a third order polynomial. So why is this noise? Right? Think about that for 1 second. The reason why it's noise is because it's more complex. Oh, I hate this when this happens. It's just sort of put me over here for the moment. Maybe I'll come back. So the reason why if this is noise is because it's more complex. And our hypothesis sets might get confused by this complexity and might see different patterns in the complexity. So this is one of these strange ideas that also happens, is that when things get so complex, sometimes you'll misread patterns. So for example, if you selected this data point and this data point, you might just think that just a flat line going straight through here would work. Or if you selected this data point and this data point, you could definitely see that a line sort of going tangent here all the way down would work. However, if this were a very simple hypothesis, if this were simply a straight line, it would be quite hard to overfit. Okay, let's explore most of these topics in a little bit greater detail. We have two types of noise. We have one type of noise that's stochastic noise. It's just sort of adding a little bit of jiggle in the y direction, in the target direction. And then we have a second type of noise, which is deterministic noise. This is that the target function is so complex, it's very easy to see patterns in it that don't exist. Okay, let's explore these types of noise. So we're going to be considering two types of target functions. One target function, which is a 10th order target. So it's a 10th order polynomial. It's pretty complex with stochastic noise. So we're adding in some stochastic noise. The second thing that we'll consider is a 40th order target polynomial with deterministic noise. So obviously it's 40th order. It's just got a lot of noise because it's incredibly complex. You can see lots of patterns that don't necessarily exist. And we'll use two hypothesis sets. We'll use a very simple hypothesis set, a second order fit, and then we will use a 10th order fit, a more complex hypothesis set. So think to yourselves one moment, what will the bias and the variance of these be? Will the bias of the second order fit be higher or lower than the 10th order fit? So the bias will be higher. There will be more error, at least on the training set, for the second order fit than for the 10th order fit. Now, will the variance for the second order fit or the 10th order fit be higher? Well, the variance for the 10th order fit will be higher. You have more hypotheses, so you have more chance to see this rare event that happens. And this rare event happening is a hypothesis misrepresenting itself because it fits to the noise. Okay, let's check this out. I have a lot of code here, so definitely do check this out. The notebook will be linked down below, so do check that out, or I might link it up here, so just check both of those. Okay, let's see what's happening. So I have one case with no noise, so absolute zero noise. What's happening here? So I've got my second order and my 10th order. The no noise will be fitting to a 10th order polynomial. So in this case, there's no, both of these, so there's a little bit of deterministic noise. The hypothesis is a bit complex, but there's no stochastic noise. Okay, so we get a train order for my second order polynomial, which is 0.07, and a test error, which is 1.6. Okay, this is pretty good. Let's check out for the 10th order. So for the 10th order, we get a train error of 6.4 to the negative 28th, and a test error of 3.7 to the negative 27th. Wow, that's pretty good. How many data points did we use in this case? Let's go check this out. So for the number of data points that we used, we've got a training set of 20 data points. This is strange, right? A 10th order polynomial fit should require how many data points, generally speaking, from a rule of thumb? Should require 100 data points to do well, whereas a second order should do extremely well in the case where it has 20 data points. This is the point, the second order, at least with 20 data points, is the point where you have less bias, or less variance, excuse me. The 10th order in this case doesn't have much variance at all. So why is this? Well, the reason is because our data set has no noise. There's no chance for it to fit to the noise. It just sees the correct pattern. And if it fits to that correct pattern, then, well, there you have it. It's going to do incredibly well on the true test set. Okay, let's add just a little bit of noise and see what happens. So we add some stochastic noise. If you're curious at the amount of stochastic noise, I believe it's here. So we're adding a normal distribution with a mean 0, variance 0.1. Okay. Let's see stochastic noise. So for our second order, once again, it's a little bit, it's actually pretty much the same. So we get a train error of 0.05 and we get a test error of 0.16. It's still fine. It seems pretty robust to the stochastic noise. Let's check out our 10th order. Our training error gets higher. Of course, as you add noise, the training error will get higher. But still, in this case, it is many times better, so not just 50 times better than our second order hypothesis, at least on the training set. However, let's check it on the test set. On the test set is sort of when it shows its very full colors. So in this case, it's going to be, 5 times worse than our test error in this case. Why did that happen? It's because it had a lot of chances to see hypotheses, or to see a hypothesis, because it's looking through lots and lots of hypotheses that misrepresents itself, that has overfit, that has seen the noise and decided to see a pattern in the noise instead of seeing the true pattern in the data. And it's very likely that it will select one of those hypotheses, so we get a much higher test error. So in this case, it's very easy to see what our approximation error is, and our generalization error, which is the difference between these two, which is massive, versus the difference between these two isn't so massive. But notice, as we add noise, the generalization error increases for both. Okay, so we have deterministic noise is the last one, and I just sort of want you to see this. We add some deterministic noise to our second order, and of course, both our training and our test errors get worse. Again, the generalization error doesn't change too much. Notice this. So a 10th order trying to fit to a 40th order polynomial, we get a small training error, but check out the test error. The test error is atrocious. And the test error is 100 to 200 times, I guess, almost 500 times worse than our test error on our second order case. So we can see that noise can exacerbate this bias variance problem. In a very noisy situation, you're going to have incredible amounts of variance. You're going to have incredible amounts of generalization error, and you need to be incredibly careful when fitting more complex hypothesis sets. Okay, so you sort of get intuitively what happens. Let's go ahead and see what happens empirically. So I've gone ahead, I've done sort of a large experiment down here that I'm going to sort of show you. Ultimately, I think the sort of thing that you want to understand from this is that this bias variance trade-off doesn't happen in a vacuum. If it did happen in a vacuum, perhaps you could find the appropriate bias variance trade-off for all data sets. Unfortunately, because each data set has its own degree of noise, both deterministic, which is incredibly hard to measure, and stochastic, which is hard to measure in itself, you need to sort of adjust the bias variance trade-off for each data set, not just for each model. So the questions, so why do complex models have higher variance? You know the answer to this. It's that we get this situation where a hypothesis misrepresents itself, and it's very likely to happen when we're searching through lots of hypotheses. Why does a hypothesis misrepresent itself? How can that even happen? We're training from the same data set. Why do some hypotheses see a true pattern, something that will happen and generalize to the test set? And why do some see a false pattern, something that won't generalize to the test set? Well, it turns out that the bad hypotheses, the ones that misrepresent themselves, they're the ones that fit to the noise. And the good hypotheses fit to the true signal in the data. Okay, so let's see this all in some final diagrams. So again, a lot of code. Please do check this out. It's kind of fun, sort of reading through this. But anyways, it's just to get these graphics down below. Okay, so here the first thing that we see is our graphic for deterministic noise. I've got sort of two colors here. I've got a red color and I've got a blue color. So a blue color is where, so again, I've got my two hypotheses. I've got my 40th order, or I'm sorry, is it 40th order? So let's see. So I've got my 10th order and I've got my second order hypothesis set. The blue areas are where my 10th order hypothesis set does better than my second order hypothesis set. So these are the areas with low variance. So where our hypothesis set is able to sort of overcome the sort of variance problem and let its great low bias shine. And down here, we've got the areas, so the red areas are where the second order hypothesis does better than the 10th order hypothesis set. Okay, so what do we notice here? and I really want to call your attention to this sort of line. So our 10th order hypothesis set always, so first, excuse me, let me explain the axes as well. So on this axis, we have the number of data points, and on this axis, we have the complexity of the target function, going all the way from, I guess, a third order polynomial all the way up to a 40th order polynomial. Okay, so what do we notice here? There's a line right at 10. So there's a line right at a 10th order polynomial, which below that, our 10th order polynomial fit always does better. So in the case where there's no stochastic noise, and we are trying to fit a 10th order polynomial with a 10th order polynomial, then yes, our 10th order polynomial will do great. There's no deterministic noise. Why is there no deterministic noise? Well, because the patterns in the data are less complex than the patterns that we can actually fit to. So if we see a pattern in the data, then we will obviously fit to the right pattern in the data. We can't see a wrong pattern in the data in this case because, one, there's no stochastic noise, and two, all the patterns in the data aren't as complex as our hypothesis in the first place, our hypothesis set in the first place, that being a 10th order hypothesis set. But then boom, as soon as we step into an 11th order hypothesis set, or an 11th order target function, the second order does much better because our 10th order starts to overfit. It starts to see hypotheses that aren't there, right? Because sometimes there's an 11th order function that we can't exactly approximate because our 10th order polynomial just doesn't have it in its hypothesis set. But instead it sees a very complex 10th order polynomial that's kind of close to this 11th order one, and it fits that instead of sort of a simpler one that captures the general pattern of the data that our second order polynomial, second order hypothesis set would do. So we see this sort of line that sort of strikes across. Not only that, but we also see this sort of point where the more data we have, the less variance that we'll have as well. So once we get up to 100 points of data, we start to see that yes, our 10th order polynomial is going to be doing much better than our second order polynomial, almost uniformly. There are a couple of exceptions, and these are just due to randomness. So yes, we see two things. So one, the deterministic the deterministic noise does make a very large difference, but only when the deterministic noise is more complex than your actual hypothesis set that you're fitting on. And then two, our rule of thumb, sort of for the number of data points for each hypothesis set, does pretty well. Okay, next one. The next one is for stochastic noise. And the pattern you see here is actually much clearer. So once again, we have blue areas where our 10th order hypothesis set does much better, and we have red areas where our second order hypothesis set does much better. In this case, it's just sort of not a straight line, but sort of a curved line that goes up. So on the left side, we have greater amounts of noise. So in this case, this is the scale of the normal distribution divided by, I believe, 100. Divided by 1,000. So we go all the way up to adding 0.2 scale in our normal distribution as noise to these Lagrange polynomials. So in this case, you can sort of notice that as we increase the noise, the second order polynomial, the second order hypothesis set will do better. However, as we increase the data points, we get this exact same pattern. The 10th order polynomial hypothesis set will do better. Okay, sort of just a plain beautiful trend. So now we actually know, and I find this quite interesting. We know exactly why the bias variance trade-off happens. And it happens because of noise. And it happens because we fit two patterns in the data that aren't actually there. Okay. So I hope you guys have enjoyed this. This was a particularly long one. This will be the last long one in our series. But I think it's incredibly important. As always, if you have any questions on what we did here, if you want to see the code, check the description. If you have any questions you want to shoot to me, please go ahead and just add them in the comments below. For the comprehension questions, I've gone ahead and I've added a few. If you would like to answer them, go ahead, write them down on sort of a piece of paper. Once done, check the comments below, see if anyone has answered them. If no one's answered them the way that you have, go ahead and sort of add your answer there and I'll respond. If someone has answered very similarly to you, just go ahead and give them a thumbs up. And as always, thank you for sort of going through this and your feedback is always welcome. So thanks once again, and I'll see you next time for how do we deal with this problem, right? So we understand that we have this problem of bias variance, and we understand we need to change the bias variance fit for our models for every data set. So how do we deal with this? Okay, next time.